Welcome back to the workshop. We will continue with Module 6 on flexible and semi-rigid pavement design strategies. We just finished explaining the transverse cracking model and transfer function. This section, or Module 6-1-3, will focus on the model and transfer function used to predict fatigue or alligator cracks in flexible pavements. There are 7 learning outcomes of Module 6.1.3, and these include define and explain the 2 types of fatigue cracking predicted in the PMED design software, bottom-up and top-down cracks. Describe the mechanisms for bottom-up and top-down fatigue cracks. Describe the fatigue strength of asphalt mixtures. Define the allowable number of load repetitions used in the fatigue damage computations. Define the incremental damage concept used for predicting bottom-up fatigue cracks. Define and explain the fracture mechanics approach used to predict top-down fatigue cracks. And finally, describe the transfer functions for both bottom-up and top-down alligator cracks. Remember the 3 topics discussed for flexible pavements. These same 3 topics are included for fatigue cracks of flexible pavements. The definition and measurement of fatigue cracks, the distress mechanism included in the PMED design software for fatigue cracks, and the transfer functions for bottom-up and top-down fatigue cracks. So let's start with the definition and measurement of fatigue alligator cracks. Fatigue cracks start in or adjacent to the wheel path as short longitudinal fatigue cracks, and then continue to grow in length in terms of longitudinal cracks, but then start to interconnect to form the area cracks defined as the classical alligator cracks. This has been the more common form of load-related cracks and the type of fatigue cracks predicted by most mechanistic empirical methods. The longitudinal fatigue cracks are measured in linear feet and then converted to an area by simply multiplying the length by 1 foot width. Alligator fatigue cracks are measured on an area basis. Longitudinal and alligator fatigue cracks are then added together and reported on a percentage basis based on the percent total lane area. There are 2 types of load-related fatigue cracks, bottom-up and top-down cracks. Both types are defined and are included as design criteria in the PMED design software. Longitudinal cracking in or adjacent to the wheel path is a form of load-related cracking. Longitudinal cracks start as short longitudinal cracks and then interconnect to form the classical alligator cracking pattern as previously defined. Longitudinal cracks are converted to an area basis by multiplying the total length of longitudinal cracks by 1 foot width. Short longitudinal cracks can start shortly after construction. However, these longitudinal cracks sometimes continue to grow in the longitudinal direction and can take much longer to form the classical alligator cracks. These types of load-related cracks can initiate at the surface and propagate downward through the asphalt layer. The downward propagation of these cracks will follow the path of least resistance through the asphalt layer. Thus, the formation of the alligator cracks can take much longer to appear for the surface initiated or top-down fatigue cracks. In other words, they increase but at a decreasing rate. Increasing but at a decreasing rate. Some industry experts believe that these cracks occur in tension and propagate in shear as wheel loads are applied to the pavement surface. Others believe that they occur and propagate only in tension. The Pavement ME design software include both shear and tension stress intensity factors in predicting top-down fatigue cracks. Not all longitudinal cracks are a direct result of wheel loads. Longitudinal cracks can also be a result of construction or placement operations created by weaknesses in the asphalt mat through the paving operation. The Pavement ME design software does not predict longitudinal cracks that are a result of construction deficiencies. For example, like longitudinal segregation or some other underlying defect or issue. So the user should not confuse the different types of longitudinal cracking in or adjacent to the wheel path, and should try to segment or separate out longitudinal cracks caused by construction deficiencies rather than truck applications or wheel load applications. Remember, Pavement ME only predicts the top-down cracking and longitudinal cracking that are a result of wheel loads. Bottom-up fatigue cracks initiate at the bottom, and propagate to the surface. They initially appear as short longitudinal cracks, but with continued truck traffic, form the classical alligator cracking. So this photograph shows the longitudinal cracks or short longitudinal cracks in or adjacent to the wheel path. With continued truck applications, the classical alligator cracking starts to appear as the longitudinal cracks start to interconnect. And then over time, with many wheel load applications, they form the more severe classical alligator cracking. Bottom-up fatigue cracks typically take time to develop, but once they start to appear at the surface, they start to increase at an increasing rate. In other words, it takes time for the classical or bottom-up fatigue cracks to appear, but once they start to appear at the surface, they start increasing at an increasing rate. In summary, it is difficult to determine if the alligator cracks are top-down or bottom-up. Top-down cracks are typically longitudinal that increase with the number of load applications, but at a decreasing rate. In other words, they increase with time. They start earlier and start to increase, but at an increasing rate. Bottom-up cracks increase in extent or area with repeated load applications at an increasing rate. Generally, it takes longer for the bottom-up fatigue cracks to appear on the surface, but once they appear on the surface and can be measured, they start to increase at an increasing rate. Now that we have defined fatigue cracks and the two types of fatigue cracks, now let's discuss the distress mechanism for predicting these fatigue cracks. The mechanism for bottom-up fatigue cracks and top-down fatigue cracks is different. So the mechanisms will be discussed separately. The best technique for separating bottom-up from top-down fatigue cracks is taking cores through cracks to determine how or where the cracks initiated and or the direction of crack propagation. Most of the sections used in the global calibration process came from the long-term pavement performance program. Unfortunately, cores for crack determination were not taken within the LTPP program. Thus, an approach or systematic procedure to determine where cracks initiated from had to come from other sources. The method that was used during the global calibration process included using the slope and shape of the time series of cracking data and an FHWA report or document. The reference for the FHWA report is displayed on this slide, report number HRT 17059, as well as the table which summarizes the overall guidance in determining or estimating whether the cracking at the surface is top-down or bottom-up. This table, or the table displayed on this slide, will be included in an expanded form on the next slide. Cores were drilled on selected non-LTPP projects to confirm the direction of crack propagation and provide some minimum verification or validation to the accuracy of the table included in the FHWA report. The table displayed on this slide was extracted or taken from the FHWA report included on the previous slide. Again, FHWA HRT 17059. It is enlarged on this slide to demonstrate the approach or procedure to separate the different types of cracks measured at the surface of the pavement. In summary, the bottom-up fatigue damage index was derived from the back calculation process of elastic layer modulus in comparison to the laboratory measured values or undamaged values and the amount of fatigue or alligator cracking observed at the surface. Those two were used to estimate whether the longitudinal and or alligator cracks are bottom-up or top-down fatigue cracks, and whether they are caused from some other type of mixture and or construction deficiency or defect. So basically, if we have higher amounts of fatigue cracking measured on a percent total lane area, and the damage index derived from the back calculated layer modulus ratio, damaged modulus versus undamaged modulus, if that is negative or very small, in all probability, the cracking observed at the surface is top-down cracking and or from some other mechanism, like debonding at the surface, segregation, or some other near-surface defect. If the percent fatigue cracking is very small or smaller to a moderate range, and the damage index ratio from the back calculation is relatively higher, then in all probability that cracking has a higher probability of being bottom-up cracking, simply because all cracks have not reached the surface or in the process of reaching the surface. However, they can also be an occurrence from lower layers exhibiting moisture damage and or debonding much further below the surface and or much lower asphalt content much lower below the surface. So it's a user's decision to decide on whether cracking measured at the surface, especially for local calibration, is a result of bottom-up and or top-down cracks. Starting with bottom-up fatigue cracks to go through the cracking mechanism and transfer function. Bottom-up fatigue crack are caused by repeated application of traffic loads. The repeated tensile strains at the bottom of the asphalt layer applied at a given point develops micro cracks that eventually form a fracture and propagates to the surface of the asphalt pavement within the wheel path. Remember the paperclip experiment from Module 2, where we failed the paperclip with multiple bends of the paperclip. In concept, the fatigue failure or cracking of asphalt layers is no different than that for the paperclip and or for Portland cement concrete that we discussed in Module 5. The fatigue strength is dependent, or the fatigue strength of asphalt mixtures is dependent upon a critical response, that critical response being tensile strain, and the fatigue strength of the material. The fatigue strength of the material is simply the allowable number of load applications or critical response applications. So in discussing the fatigue cracking mechanisms, we're going to separate the discussion into three parameters or variable, similar to the paperclip experiment that was illustrated in Module 2. First will be the critical response calculation, then the material strength of the asphalt mixture, and then the allowable numbers of load applications or repetitions. As previously noted earlier in this module, Module 6, as well as in Module 2, Julia is an elastic layer program that the Pavement ME design software uses to compute the critical pavement responses. Julia is used to calculate the critical pavement responses for predicting bottom-up fatigue cracking. Bottom-up fatigue cracks are a result of repeated tensile strains at the bottom of the asphalt layer. The horizontal tensile strain is dependent on Poisson's ratio of the asphalt layer, the layer thickness or total thickness of the asphalt layer, the stiffness or dynamic modulus of the asphalt layer, as well as the stiffness and thicknesses of the supporting layers. In other words, any type of base material and subgrade strata supporting the asphalt concrete layer. Now let's identify the asphalt mixture fatigue strength that is measured in the laboratory using the flexural bending beam fatigue test to predict bottom-up fatigue cracks. Remember, the fatigue testing of asphalt mixtures was discussed in Module 4-4-5 on asphalt mixtures. For PCC mixtures, as we discussed in Module 5, the ratio of tensile stress to modulus of rupture was used to estimate the number of load applications to failure for all types of Portland cement concrete mixtures. For asphalt mixtures, the tensile strain and modulus are used, but there is no normalization procedure of the applied pavement response variable like it is for Portland cement concrete. So the applied tensile strain, and then the number of cycles to failure, which is 50% of the initial flexural modulus, is defined as failure in the laboratory, is used to determine the allowable number, or used to determine the fatigue strength of the asphalt mixture. And an example at different temperatures and strain levels is shown on this slide or in this graph. Very simply, AASHTO T321 is used to estimate the number of load applications to failure as defined in the laboratory. As displayed in the graph, the tensile strain applied at a specific temperature or modulus is measured to determine the number of load repetitions to failure. Remember from Module 4-4-5, there are different definitions of failure in a laboratory beam specimen as defined in AASHTO T321. For the MEPDG, the definition of failure, as just mentioned, is the decrease in the flexural stiffness of the asphalt beam to a value of 50% of its initial flexural stiffness at the start of the test. So the fatigue strength of an asphalt mixture is dependent upon the tensile strain applied and the flexural stiffness of the beam specimen. A range of test temperatures are used as displayed in the graph for convenience and is directly related to modulus. In other words, the important variable is the flexural modulus. The temperature of the beam specimen is used in the laboratory because it's controllable and remains constant throughout the test. In summary, the asphalt mixture fatigue strength measured in the laboratory is simply the allowable number of load applications, which was displayed on the previous slide and shown on this slide. So the mixture fatigue strength is simply the allowable number of load applications for a specific tensile strain level and temperature. The regression equation displayed in this slide is the outcome of many fatigue tests conducted in accordance with or similar to AASHTO T321. The fatigue strength or allowable number of load applications is dependent upon the applied tensile strain, dynamic modulus, and other material and structural variables. The C variable is the volumetric property effect and is dependent on its effective asphalt content by volume and the percent air voids of the test specimen. So the fatigue strength or allowable number of load applications to failure in the laboratory will also be dependent upon the air voids and asphalt content of that beam specimen. The CH variable is the structural thickness effect and is dependent upon the asphalt layer thickness. as shown in the slide. The fatigue testing using repeated load flexural beams can be highly variable and very difficult to analyze, especially when a relatively few number of beam specimens are used to measure the fatigue strength in the laboratory. As mentioned in Module 445, a standard practice was prepared for AASHTO to provide guidelines for interpreting the outcome from the fatigue strength test to derive the fatigue strength coefficients of the bottom-up fatigue cracking transfer function that are entered in the PMED design software. The AASHTO standard practice is available from AASHTOware. So the fatigue strength parameters, as noted in Module 445, are simply the K coefficients or variables in the allowable number of load applications regression equations. And we'll discuss these in more detail a little later in this module. So these are the variables, the KF1 from the laboratory, that are entered into the PMED design software, and they're derived from the laboratory testing of different asphalt mixtures with different conditions. As also mentioned in Module 445, a surrogate test has been used to derive the bottom-up fatigue cracking transfer function because of three major reasons. First, AASHTO 321 can exhibit a lot of variation in the test results between the tensile strain level and temperature, as was displayed on the previous slide. Preparing beam specimens, test specimens, is critical and needs to be absent of any test specimen defects. The time to test the bending beam specimen, really the time to prepare and test the bending beam specimens to failure, can take a lot of time and is very labor intensive. As such, the indirect tensile strength, failure strain, and dynamic modulus test has been used to estimate the coefficients of the bottom-up fatigue cracking transfer function. In other words, the indirect tensile strength and dynamic modulus test are used to estimate the fatigue strength parameters of KF1, KF2, and KF3 in the laboratory. The indirect tensile strain failure and dynamic modulus test, measuring the indirect tensile strain at failure from an indirect tensile strength test, strain versus stress, and the dynamic modulus of an asphalt mixture measured in the laboratory, dynamic modulus measured in the laboratory, are the two parameters used in estimating the fatigue strength coefficients. The indirect tensile strength is measured in accordance with ASTM D6931 as displayed to the chart on the left of the slide. ASTM D6931 is modified to add the LVDTs to the faces of the indirect tensile specimen and measure the horizontal and vertical displacement in accordance with AASHTO T322, but at the intermediate or fatigue test temperatures. The measured horizontal displacements of the specimen are used to determine the tensile strain at failure for multiple test specimens and even at different test temperatures. The Uniaxial dynamic modulus test, or the triaxial dynamic modulus test, is measured in accordance with AASHTO T378, as displayed in the chart to the right. A loading frequency of 10 Hertz is used because 10 Hertz is used in AASHTO T321. A dynamic modulus test was discussed in an earlier section of this module, as well as also in module 445. The two test outcomes are combined to determine the relationship between tensile strain at failure, and dynamic modulus, as displayed in the lower graph. This relationship is used to estimate the coefficients of the bottom-up fatigue cracking fatigue strength equation. The standard practice prepared for AASHTO provides more detail on deriving the fatigue strength coefficients from the indirect tensile strain at failure and dynamic modulus of the asphalt mixture in terms of the relationship between that failure strain and modulus. The regression equation displayed on this graph is the outcome of many fatigue tests conducted in accordance with AASHTO T321, as was previously mentioned. The fatigue strength or allowable number of load applications is dependent upon the applied tensile strain, dynamic modulus, and other material and structural variables. The C variable is the volumetric effect. If you remember from a previous slide within this module, and is dependent on the effective asphalt content by volume and the percent air voids of the test specimen. The CH variable is the structural thickness effect and is dependent upon the total asphalt layer thickness, which was included in a previous slide within this module. The fatigue testing using repeated load flexural bending beams can be highly variable and difficult to analyze, especially when a relatively few number of beam test specimens are used to measure the fatigue strength. As measured in Module 445, a standard practice was prepared for AASHTO to provide guidance for interpreting the outcome of the fatigue strength test to derive the fatigue strength coefficients of the bottom-up fatigue cracking transfer function to be entered in the PMED software. And as mentioned previously, the AASHTO standard practice is available from AASHTO. So the K coefficients and beta coefficients, the beta coefficients are the global calibration parameters from the laboratory fatigue test. The K coefficients, KF1, measured in microstrains, KF2, and then KF3. And then the beta coefficients for relatively thin asphalts, less than 5 inches in thickness. And then that beta coefficient is thickness dependent. So it's constant for less than 5 inches in thickness. It's also constant for greater than 12 inches. But then it is for the thickness from 5 to 12, the beta coefficient is defined based on the thickness of the asphalt layer, the total thickness of the asphalt layer. The beta calibration coefficient for the term KF2 and KF3 are also constant. So the fatigue cracking mechanism includes calculating the asphalt layer incremental fatigue damage and summing it to determine total fatigue damage over time, regardless of which laboratory test is used to determine the allowable number of load repetitions. And that is the fatigue damage accumulation is determined in the same way. So it's determined in the same way regardless of which laboratory test was used to determine the allowable number of load application. This section of the module will explain and discuss the accumulation of the incremental fatigue damage in the asphalt layer, which is similar in concept to that has been discussed for Portland cement concrete in Module 5-1-1 for mid-slab fatigue cracking in rigid pavements. First, what does the incremental fatigue damage accumulation mean and how is it determined? Remember from Module 2, as well as from Module 5 for rigid pavements, the fatigue damage is a result of the actual number of load applications divided by the allowable number of load applications, just like what was demonstrated from the paperclip experiment. So it's the actual number, little n, of wheel load applications divided by the allowable number of load applications, or the fatigue strength of the asphalt mixture. The incremental fatigue damage is summed using Miner's hypothesis or damage equation, just like for Portland cement concrete mixtures. The damage is calculated based on the critical responses, tensile strain, computed by the Julia elastic layer response program. Tensile strain is calculated at the bottom of the asphalt layer at critical locations based on the axle load geometry and weight within each time increment. Many of the other pavement inputs also vary throughout the year and have an impact on the calculated tensile strain. For example, the stiffness of the underlying subgrade and the stiffness and thickness of any underlying aggregate base and or subgrade layers and whether they're stabilized all have an impact on the calculated tensile strain. In summary, the design life is divided into time and load increments. Some of the pavement and traffic variables that change over time, for which the pavement ME design software considers, include asphalt dynamic modulus, which increases over time because of aging. The aging is dependent upon the asphalt layer depth and volumetric properties. Temperature gradients change throughout the day and season or month. Temperature gradients have an impact on the dynamic modulus. The number of axle load applications also increase over time, and the different types of trucks have different axle tire geometries, all of which have an impact on the calculated tensile strain. The unbound aggregate base and subgrade elastic modulus values vary over time depending upon the degree of saturation of those unbound layers. As such, the pavement ME design software is an extensive bookkeeping process to calculate and accumulate the fatigue damage of the asphalt layer over time for designing flexible pavements. In summary, the fatigue damage is calculated throughout the design period considering the variables listed and noted on the previous slide. The fatigue damage for top-down longitudinal cracks are listed, or the fatigue damage for the bottom-up longitudinal and alligator fatigue cracks are listed in the output report, which is graphically illustrated in the figure displayed on the slide. So the program, when included in the output report, provides the bottom-up damage that's calculated throughout the design period. So the user can review the amount of bottom-up damage at any point in time. The PMED design software calculates the maximum accumulated fatigue damage over time using Miner's hypothesis, or the fatigue damage concept, as was explained in the previous slides. But how does the fatigue damage get used to design fatigue pavements to limit the percent cracking of total lane area, or total lane area fatigue cracks? The answer is through the transfer functions as defined in Module 2. So, moving on to explaining the transfer functions for fatigue cracking of flexible pavements. Remember from Module 2, the critical pavement responses are used to determine or calculate fatigue damage. And the transfer function converts the fatigue damage to what we can see and measure on the pavement surface. For bottom-up fatigue cracks, that is the percent total lane area of cracking. This graph displays an illustration of the transfer function for bottom-up fatigue cracks of flexible pavements. The transfer function is defined through the calibration process by relating the accumulated bottom-up fatigue cracking damage to the percent total lane area of cracking measured at the surface for different flexible pavement sections. For each increment of percent cracking, the calculated bottom-up fatigue damage is related to the percent cracking observed at a specific test section and point in time. And all of the data is then compared and are used to define basically the transverse function relating the damage index from bottom-up fatigue cracking to what we can see and measure on the pavement surface, percent total lane area with bottom-up fatigue cracking. The graph included in this slide is the outcome of relating the bottom-up fatigue damage and the percent cracking total lane area measured or observed on actual flexible pavements, predominantly within the long-term pavement performance program. The bottom-up fatigue damage the cumulative bottom-up fatigue damage at the bottom of the asphalt layer is calculated and then converted to a physical distress percent total lane area of bottom-up fatigue damage through the distress to damage transfer function, or the calibrated distress damage to distress transfer function. This slide is a graphical representation of the process or procedure used to calculate the amount of bottom-up fatigue cracks. In summary, the fatigue damage is calculated over the design life for a specific flexible pavement cross-section, input variables, and site factor. The transfer function is then used to convert the fatigue damage to a measured cracking value. The amount of fatigue damage is then displayed by fatigue cracking predicted over time throughout the design life. The bottom-up fatigue cracking transfer function is displayed on this slide along with the allowable number of wheel load applications, or the fatigue strength of the asphalt layer. So the bottom-up fatigue cracking transfer function, and then the fatigue strength equation or allowable number of load applications for a specific condition. Remember, the bottom-up fatigue cracking damage is defined using Miner's hypothesis of the actual number of load repetitions, little n, divided by the allowable number of load applications, big N. The C coefficients, the different C coefficients will be of the transfer function will be explained and defined on the following slide. So the C1 prime, C1 to prime, and the C2 prime are defined by the total asphalt layer thickness and are related to the stress versus strain controlled conditions of a flexible pavement. The C1 and C2 parameters will be defined and explained on the next slide. But C1 and C2 are global calibration parameters or result from the calibration process. This slide summarizes the calibration coefficients of the transfer functions. In other words, C1, C2, and C3 that were derived from the global calibration process for bottom-up fatigue cracking. The global calibration coefficients, as we just mentioned, are C1, C2, and then C3. C2 is dependent upon the asphalt layer thickness, or the total asphalt layer thickness, as shown in the table. As mentioned previously, the values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice, depending on the results of the calibration. The coefficients and exponents of the transfer function, however, are also included in the output report for the Pavement ME design software. So calibration coefficients C1 and C3 are constant. Calibration coefficient C2 is dependent upon the layer thickness or the total layer thickness of the asphalt. For values less than 5 inches or relatively thin asphalt pavements, C2 is constant, and values greater than 12 inches of total asphalt layer, which is a relatively thick asphalt pavement, C2 is constant. C2 from 5 inches to 12 inches is thickness dependent, which is calculated by the software and or used by the software in predicting total accumulated fatigue damage. Now, it is important to remember the volumetric property impact on the allowable number of load applications or fatigue strength of the asphalt layer. The asphalt content and air voids, as well as the dynamic modulus of the asphalt mixture, have a significant impact on the allowable number of load applications and need to be included in determining the fatigue strength or K values of the asphalt mixture tested in the laboratory. So from preparing different beam specimens or indirect tensile test specimens, the volumetric condition of those test specimens need to be taken into account in deriving the K1, K2, and K3 coefficients for the allowable number of load applications that are used. Remember from Module 3 on reliability, the residual errors between the predicted and measured distresses, bottom-up fatigue cracks, are used to determine the standard deviation of the residuals to determine the reliability for bottom-up fatigue cracks, which is included or displayed on the slide. So we start with tensile strain at the bottom of the asphalt layer. That response variable through the damage index is converted to the measured total fatigue cracking, bottom-up fatigue cracking, and then the reliability level is in to determine the bottom-up fatigue cracking at different reliability values based on the average or the 50% reliability condition. Reliability, as we just mentioned, was discussed in detail in Module 3 and how it's applied in the pavement ME design software. The standard deviations or the residuals of bottom-up fatigue crack is displayed on this slide. Standard deviation of the residuals for bottom-up fatigue cracks. The standard deviation of the residuals is used to determine the reliability of the flexible pavement design relative to bottom-up fatigue cracks. So before we go forward, do not get bottom-up fatigue cracks or alligator cracks mixed up with top-down fatigue cracks or other cracks that occur from some other layer defect like segregation, layer debonding, or other construction deficiency, because that will have a significant impact on the resulting C factors in the fatigue cracking, bottom-up fatigue cracking transfer function. So these bottom-up versus other types of cracking need to be clearly defined and discriminated against or segregated for the different types of cracking. So now let's move on to top-down fatigue cracks in terms of explaining and reviewing the mechanisms and transverse cracks or transfer functions. Before getting into the details of top-down cracking model and transfer function, the MEPDG Manual of Practice, specifically the 2021 supplement, includes an overview of the prediction methodology of top-down fatigue cracks for flexible pavement design. So now let's open the MEPDG Manual of Practice, specifically the 2021 supplement, to briefly go through the new section 5.1.3 on top-down cracking. So we'll go to section 5.3.3 on load-related cracking. The load-related cracking, fatigue cracking, specifically top-down cracking, is what was changed for the 2021 supplement. So the 2021 supplement provides an overview and discussion of the fracture mechanics approach using the Paris law for fracture propagation to characterize the crack growth due to repeated load applications. And that is identified and discussed in this 2021 supplement. So the user is basically encouraged, or the designer is encouraged, to review this supplement so that he or she understands the mechanisms and transfer functions that are used to predict top-down fatigue cracks in flexible pavement design. So now let's go back to the presentation and basically continue. So the fracture mechanics approach is used for predicting top-down fatigue cracks, similar to the process that was used and explained for predicting transverse cracks, which was discussed in Module 6-1-2. The discussion and explanation for fatigue cracks is grouped into three parts in this session: crack initiation and time to crack initiation, crack propagation, and the transfer function for top-down cracking. A fracture mechanics based model or approach is used to calculate the incremental growth in crack depth, and crack depth is sometimes referred to as crack length due to repetitive traffic loadings using the Paris law. A two-part prediction methodology is used in the PMED design software: the crack initiation and then crack propagation. So the cracks first initiate, and then once the crack initiates, the second part, using fracture mechanics, then drives the crack downward into the pavement layer. Stress intensity factors. Stress intensity factors for single and dual tire loads are calculated to estimate the downward growth of crack propagation for each month in the pavement design life. The stress intensity factors are dependent on the type of wheel load geometry, single versus dual loads, of the axle itself. An item to remember in reviewing various publications on this topic of top-down fatigue cracking is related to its use in the PMED design software. The term of crack length versus crack depth. Crack length is sometimes used in the research documents. However, the term crack depth is applied to the downward growth of top-down cracking. So crack length and crack depth can mean the same thing in PMED design software. However, crack depth is the specific term used for determining how fast or slow the crack initiated at the surface propagates downward through the asphalt layer. Transverse or fatigue cracks are calculated or reported on a percent area basis, similar to the bottom of fatigue cracks that we just discussed. Another important assumption used in the PMED design software is that the crack width at the surface was used to define crack depth from a calibration standpoint. The wider the crack, the deeper the crack growth. That assumption was used for calibration in the PMED software. Crack depth is not reported or measured within the long-term pavement performance program. So the crack width and or geometry was used to define crack depth, because crack severity is included in the long-term pavement performance database. So crack severity is tied to crack width, and then crack width is tied to crack depth to define some of the calibration parameters of the fracture mechanics method or approach. Similar to rigid pavement model discussed in Module 5 for calculating the structural responses, a finite element program was used to calculate the stress intensity factors for a wide range of structures, materials, and site condition factors. For example, different traffic loads, different axle geometry configuration, different material properties, different layer thicknesses, different support conditions for flexible pavements. The results or outcomes from these computations were used to develop artificial neural networks to calculate the stress intensity factors used within the PMED design software for simplicity and computational speed, just like the artificial neural networks developed for rigid pavements. Since the responses or stress intensity factors from a finite element program was used to develop the artificial neural networks, it is important to recognize the assumptions and boundary conditions used in those responses. In summary, the pavement structure was composed of 3 layers: an asphalt layer, an aggregate base layer, and a subgrade layer. All pavements with multiple asphalt layers were converted to an equivalent 3-layer structure for which the asphalt layer was the most important. All asphalt layers were combined into 1 layer, but the properties for the wearing surface controlled and/or were used for top-down cracking. 1 aggregate base layer was used, so different combinations of the aggregate bases were combined into 1 layer. And then 1 subgrade soil strata was used. So when different soil strata are located below the asphalt surface at a specific test sections, those subgrade strata were combined into 1 layer for top-down fatigue cracks. The top-down fatigue cracking model, thus, is composed of 2 parts. The first part is crack initiation, or the cracks just start to occur at the surface, and then crack propagation. How slow or fast do those surface-initiated cracks propagate downward through the asphalt layer? As mentioned previously, the crack depth established over time is related to crack width or crack severity as documented or recorded in the long-term pavement performance database. The reason for that assumption is that crack severity is included in the LTPP database, while crack width, specifically in crack depth, are not. So crack width is tied to crack severity in the LTPP database and was used to estimate the depth of the top-down cracking. So crack initiation is at a crack depth, or assumed to be at a crack depth of 0.3 inches, or 7.5 millimeters. So the program goes through a process to determine how long or much time or the number of load applications does it take to initiate the crack at the surface. The depth of that crack at the surface is assumed to be 0.3 inches. So the time to crack initiation, T0, is calculated from an regression equation, which is a function of average annual daily truck traffic, climate data, and asphalt material properties. The number of months to failure is defined as N sub F. In other words, the time required for that surface-initiated crack to grow from 7.5 millimeters, or 0.3 inches, to 40 millimeters, or about 1.5 inches or so. The number of months to failure is then used to determine the top-down cracking scale for determining the maximum top-down cracking length and or depth, and the shape or the rate of growth of top-down cracking over time. In other words, the top-down cracking distress curve. The crack initiation is not included in the LTPP database, as we previously mentioned, or in any other data set when the global calibration process was completed for top-down cracking. As such, the time to crack initiation had to be backcasted using the time series data for top-down cracking. So as an example of this backcasting procedure, or an example of this backcasting procedure is illustrated on this slide. The procedure used the longitudinal cracks to begin with because they are the first type of load-related cracking to appear on the surface or to be measured on the surface. The overall mathematical form or relationship for top-down fatigue cracks was then used to backcast the time to cracking and to crack initiation, defined as T sub naught. And this simply shows one example where the top-down cracking length of longitudinal cracks in feet per mile were used to estimate the time at which they started to appear at the surface. This is a schematic illustration of how that process was done for determining the time to crack initiation. So it's initially based on longitudinal cracks, but the final version in the software uses total cracks or percent total lane area. So the longitudinal cracks initially used were converted to a percent total lane area as previously discussed within this module. The calibration coefficients for the time to crack initiation regression equation are displayed on this slide. So there is a KLR1, KLR2, KLR3, KLR4, and KLR5 coefficients that were derived from the global calibration process to determine the time to crack initiation. That is dependent upon a term called the energy parameter, A0 divided by 2 capital A subscript O, as well as the average annual daily truck traffic, and the annual number of days above 32 degrees centigrade and the annual number of days below 32 degrees centigrade. In other words, the HT and LT parameters. The energy parameter is also shown on the slide and is a function of the relaxation power law function parameters for aged asphalt. E1 is simply a modulus term of the asphalt, and M2 comes from the basically from the relaxation modulus power law function. So both of the terms are mixture dependent upon the wearing surface of the test section or section. HA is simply the total asphalt layer thickness itself. And the global calibration parameters for the time to crack initiation regression equation are simply displayed on this slide. So these are the global calibration parameters, the capital K values for L1, L2, L3, L4, and L5, and these are the values derived or the outcome from the global calibration process shown on this slide. The propagation of the surface fatigue or load-related cracks is like the transverse cracking model based on the fracture mechanics approach. However, a modified Paris law is used to propagate the surface cracks downward through the asphalt layers, specifically using the pseudo JNR integral, as shown on this slide. The properties of the asphalt layers determined for the upper asphalt layer. The upper asphalt layer, not for the lower asphalt layers. A prime and N prime are the fracture parameters which will be discussed and displayed on the following slides. So the pseudo JNR integral and the fracture parameters are used to define the change in crack width, the change in crack depth versus the change or increase in the number of load applications over a specific time interval. So DC divided by dN defines the rate of how that top-down crack initiation will propagate through the wearing surface and through the lower layers of the asphalt based on the properties of the wearing surface. The pseudo JNR integral is defined as the increment in dissipated work per unit crack surface area and is related to or determined by three modes of the stress intensity factor and Poisson's ratio and the representative elastic modulus of the asphalt wearing surface. So the asphalt wearing surface, again, not the lower asphalt layers, but the asphalt wearing surface. As displayed on the core, the crack depth is not restricted to the upper 1.5 inches of the asphalt layer. As mentioned previously, some industry experts believe and have reported that the top-down crack depth will be restricted to the upper 1.5 inches. Various cores from multiple projects have been drilled to confirm that the crack propagation from top-down cracking is not restricted to the upper 1.5 inches and can propagate into and below the wearing surface into the lower asphalt layers themselves and can propagate much deeper, which is defined by the properties of the asphalt wearing surface. So the pseudo JNR integral, as just mentioned, is dependent upon Poisson's ratio, a representative elastic modulus of the mix, and then the K1, or the stress intensity factor in mode 1, which is the opening mode, K2, which is the stress intensity factor of mode 2, that's the end plane shear at the crack, and then K subscript 3, which is the stress intensity factor from mode 3, which is the out of plane shear. So all three types of stress intensity factors are used to determine how the crack that initiates at the surface propagates through the asphalt layer itself. And it is not restricted to the upper 1.5 inches of the asphalt. The asphalt fracture parameters are displayed on this slide. Similar to bottom-up fatigue cracks, the volumetric properties of air voids and asphalt content have an impact on the fracture parameters and thus on the occurrence of top-down fatigue cracks. So N and A fracture mechanics of the fracture mechanics approach are determined and shown on this slide. The N parameter or exponent is dependent upon the shape parameter of the aggregate power law function, in other words, the aggregate blend or the gradation of the aggregate blend, as well as the E1 and M, which are the relaxation modulus power law function parameters, again for aged asphalt, and also on the average air voids and or average asphalt content by total weight of the mix. Not the effective asphalt content, but the total asphalt content by weight of mix. Those are used to determine N. The A fracture parameter is dependent upon N, so it is also dependent upon the other material properties of the wearing surface. Gradation definitely impacts the area of top-down cracking, and the field data from the LTPP program confirms that impact. The graph included in this slide displays the area of alligator cracking for those sites which were found to exhibit top-down cracking, which is on some of the SBS 9 sections included in the LTPP program with different gradations. The more coarse graded aggregate blend, with higher permeabilities, the greater the area of alligator cracking in terms of percent total lane area. The higher the coarse graded mixtures, as exhibited with the X, exhibit more top-down cracking than for the fine graded mixes exhibited by the circles. For this one site or a couple of sites as an example. So gradation on whether it's coarse, fine graded through the aggregate shape factor definitely has an impact on the amount of top-down cracking predicted for a specific asphalt mixture. The transfer function for predicting the area of top-down cracking includes a sigmoidal function and is based on the maximum area of top-down cracking and the time to top-down cracking, as well as the scaling shape parameter and calibration coefficients. The rho and beta terms will be defined on the next slide. But the T0 is the time to crack initiation in days. The C1, C2, and C3 are calibration coefficients, and the rho and beta, which will be defined on the next slides, are simply the scaling shape parameters. The rho variable or constant is a function. The rho variable is a function of climate. The C1 and C2 and C3 calibration coefficients are also defined on this slide and derived from the global calibration process. The rho variable or constant is a function of climate and the number of months to failure, designated as capital N sub F. Or the top-down crack propagation to a depth of about 1.5 inches. The beta function, or constant, is the number of months to failure. Alpha, so for rho, alpha and beta are defined by the climate, and we will define those values in the next slide, as well as the number of months to failure, or to a crack depth, which is defined at failure, to a crack depth of about 1.5 inches. However, that does not mean that the crack depth stops at 1.5 inches. The program will continue to propagate that cracking below 1.5 inches. This is just defining the time or number of months to a specific depth. And then the beta is also a function of the number of months to failure. The climate parameters are defined by the number of days above 32 degrees centigrade and number of days below 0 degrees centigrade. The enhanced integrated climatic model is used to determine the climatic zone and provide the information for a specific project location. Remember, climate was discussed in Module 442 in terms of the inputs to the Pavement ME program. So the climate zone uses the ICM data to determine the climatic zone for a specific project zone in the pavement for predicting top-down fatigue graph for top-down fatigue cracks. The number of days above 32 degrees centigrade and below 0 degrees centigrade are used and calculated as the average number below and above specific temperatures from the hour climatic data. And those conditions, the alpha and the A shown in the table, are then used to calculate rho. Reliability was discussed in detail in Module 3 and how it is applied in the Pavement ME design software. The standard deviation of the residuals of the area for top-down fatigue cracks is displayed on this slide. The standard deviation of residuals is used to determine the reliability as related to the area of top-down alligator cracks in flexible pavements. Kind of as a side note, what's shown here is using the maintenance option in the Pavement ME software to indicate that top-down fatigue cracks can be impacted or dependent upon whether the maintenance activity is simulated in the Pavement ME software. So top-down fatigue cracks is influenced by using some type of maintenance activity simply because those cracks are surface-related cracks or initiate at the surface. So now let's move on to the summary. This section is a summary of the materials presented under this module, Module 613, for fatigue cracking of flexible pavements. In summary, bottom-up fatigue cracks are a result of repeated bending or repeated tensile strains at the bottom of the asphalt layer. Top-down fatigue cracks, or surface-initiated fatigue cracks, are caused by the applications of height tire pressures and heavy wheel loads in combination with thermal tensile stresses and strains, and which are caused by a drop in pavement temperature as well as with wheel loads. Again, these cracks are not restricted to the top 1.5 inches and can propagate deeper below 1.5 inches. It is difficult to determine if the alligator cracks are top down or bottom up cracking at the surface without the use of cores. So remember, top down cracks are typically longitudinal cracks converted to on an area basis to alligator cracks with the number of wheel loads or over time. So top-down cracks exhibit an increase in the amount of cracking but at a decreasing rate. Bottom-up fatigue cracks increase in extent or area with repeated wheel load applications, but increase at an increasing rate. So top-down cracks are dependent upon how changes in the asphalt wearing surface, especially at the surface, for crack initiation on number of months it takes to initiate a crack at the surface, whereas that is not done at the bottom of the asphalt layer for bottom-up fatigue cracks. Both are caused by and determined by wheel load, so they are both wheel load related cracks. Top-down fatigue cracks have a greater impact from the stiffness gradients near the surface because of the temperature gradients near the surface. Another difference between the bottom-up and top-down fatigue cracks models in the PMED software is that the software predicts area and load-related fatigue cracks or alligator cracks for top-down, while it only predicts the area of alligator cracks. So for top-down cracking, the program predicts area and depth of the alligator cracks. This is beneficial because the user could see how fast the crack, or can see how fast the cracks are propagating downward through the asphalt layer, and whether they're just confined to the surface on the average for using the maintenance strategy, as compared to bottom-up fatigue cracking, where only area of alligator cracks are predicted for bottom-up fatigue cracks, because we can't really see what's going on at the bottom of the asphalt layer below the surface. Remember, there are other forms of local cracking that can occur from construction defects or deficiencies. These include longitudinal or truck-to-truck segregation, layer debonding, and or stripping. These localized defects, deficiencies, which can result in early cracking, are not considered in the PMED design software. So in summary, we defined and or explained the two types of fatigue cracking predicted by the PMED design software, bottom-up and top-down fatigue cracks. We discussed the mechanisms for both bottom-up and top-down fatigue cracking. We described the fatigue strength of asphalt mixtures. We defined the allowable number of load applications used in the fatigue damage computations. We defined the incremental damage concept used for predicting bottom-up fatigue cracks. and we defined and explained the fracture mechanics approach used to predict top-down fatigue cracks. And in summary and final, we described the transfer functions for bottom-up and top-down alligator cracks. So this concludes Module 613 on fatigue cracks and flexible pavements. The next submodule of the training course sequencing is Module 614 on IRI smoothness degradation or flexible pavements.